Hello everyone and welcome back to Minic Analytics. In this video, we will be exploring how we are going to be using the principal component analysis. So during my search here and there, so I found out that PCA is a very important element in machine learning. And so in today's video, we are going to see how we are going to apply the principal component analysis as part of as part of a tool to be used in machine learning. So before we get started, if you're new to this place, we are welcoming you to this wonderful community. That's subscribe to our channel, hit the notification bell so that you never miss any of our video updates. Without further ado, let's get started. So in machine learning, most of the problems that you will be encountering when solving machine learning problems will be problems that will entail using a lot of there will be problems that will be having a lot of features that you will need to work with. So having these many features that you're going to be working in those problems that you will be solving, there comes in the principal component analysis, which is a dimensionality reduction technique. So you'll be using that to be able to reduce the dimensions of your data. And with the principal component analysis, what you are basically doing is that you are identifying a hyperplane in the feature space, and this hyperplane is chosen to be the one that lies closest to your data points. And when the hyperplane is lying closer to your data points, what essentially we are saying is that we are trying to minimize the sum of square distance between the data points and the hyperplane. Okay, so the advantage now of using the principal component analysis is that it's going to allow for the effective dimensionality reduction of your data, and in the process preserving the essential information present in your data. Also, another thing with the principal component analysis is that by reducing this feature space, you will be increasing the time that will be required for training your models. Okay, so basically that's what you're going to be doing today, and having a brief introduction in what we are going to be doing today. So let's jump in and get started. Okay, so as usual, we'll start by importing the libraries that we will be using. So I'm going to import. So import the libraries. I'm going to import these libraries. So import the libraries. So I'm going to start import pandas. So I won't be using a lot of many of these libraries because this is something like a how-to video. So I will try to minimize on the extent on how I will proceed with this. So I will also import NumPy. So NumPy as NP. For let's say for visualization, we can use matplotlib. Matplotlib. Okay, so basically those are the libraries that we'll be using. Then after this, we can then import the datasets. So I'm going to import the dataset. This is the dataset that we'll be using. Okay, so you can see we have a total of so when using the head method, so it just prints out the first 5 rows of your data frame. So you can see we have these are the five rows. Then you can see we have 5 rows, and so our data frame contains 114 columns. So when we say a feature space, so we can say that we have a lot of columns, and these columns are the features. So we definitely have a high feature space. That's why we are going to see how we will use the principal component analysis to help us try to reduce these dimensions and speed up our training process. Okay, so I'll move on to data summary. So just to see what we are dealing with. So in terms of, so with the data summary, we're just going to have a brief overview of our data. So brief detailed overview of our data. So we can see from our data frame, we have a total of 20,468 entries. So these are the number of rows in our data frame. In terms of columns, we have 114 columns, as we saw earlier. You can see we have many columns in our data frame. Okay. In terms of the different data types, you can see the memory usage. So I'm going to perform some checks to see if our data is okay. So I'll start with checking for missing values. So checking for missing values. So I want to see if we're missing values in our data. Because we have a lot of columns, because we have a lot of columns, the features, 114. So I will just try to loop through every column in our data frame and just to fish out to see if we have some missing values, missing values in those columns. So for column in df.columns, so I'll just use a simple for loop to perform this operation. So we are missing for missing values. We're checking for missing values. So missing values. So df column. So column dot is null. Then we'll just sum. So we are going to check for that. Null should be a function. So this null is supposed to be a function. Then, so if we are missing values, so if you're going to be missing values greater than 0, so if then we are going to print. So basically, this is just a not a function. It's a loop inside another loop. I'll say that. So we're going to print and say that. So I'll use an f string. So column f column. Then okay, so that's it. Goes to something here. So it work. So column this one, okay. Now we're okay. So supposed to be 1. So this one has this, if that one has missing values. And okay, now it's okay. Then we'll just use a break statement here. So this is our if block, but will require an else statement. So else, basically it will be telling us that if we don't have, let me comment here and say that this block will only execute if the loop completes without a break statement. So basically we are looking for missing values, and this is what we'll be using to check for those missing values. So if we won't encounter any missing values, then the whole of this code will be interpreted. So we won't break outside this loop. So since we're not going to break from that loop, then we can just print a statement saying that we don't have there are no missing values. Okay, so I'm going to execute this. We have break this. So you can see that our data frame does not contain any missing values. Okay, so after checking for the missing values, I would like to drop the first column, this column, the unnamed column. So I don't see the usefulness of that column. So I'm just going to drop columns. So for this column, I'm going to use the df.drop. I'll just drop this column. It is unnamed. So unnamed. Okay. Axis equals 1. Then when we run this again, you can see that we don't have, so we have dropped that column from our data frame. Then after this, you can then move to the next step, which is about, let's see the distribution of the labels in our target variable. So let's see, checking for distribution of let's say classes in target variable. So here, just say labels. So our target, so the column target is our target variable. So let's just check. So value counts, then reset index. So set index. So just so for the targets we have, so this is a binary classification. So we only have two targets, so 0 and 1. But in terms of the count, you can see that class 0 is majority, while class 1 is the minority. So let's see if maybe it will affect, but our classification, the classification part, but that is beyond the scope of this video. We're just dealing and seeing how we are going to apply the principal component analysis, the PCA. So after this, let's define the features and the target variable. So here, so x will be the features. X for the x's, so df will just drop the column targets, columns So we just drop the columns targets from our features. Okay. So this is it. Then for our y, I will just so y is a target variable. So our y will just be the column targets. So this is, so we have now split we have now defined the features as well as the target variable. Then after this, let's import the standard scalar. So import the standard scalar. So obviously there are different types of ways to scale your data, but let's use the most common one, the standard scalar. So from sklearn this is pre-processing we're going to import standard scalar. Then let's initialize the scalar. So scalar. So let's okay, so we initialize the standard scalar, and after this we can now fit and transform the features. Fit and so here we are now we are going to standardize all our features. That's why we did this separation. So we won't be affecting any of our the values in our target variable. The only values that you're going to be standardizing will be the values from the feature variable. Okay, so we standardize this, and then we apply our principal component analysis. We apply the principal, the PCA. Okay, so after, so let's fit. I'll just call this as scale. This one is slightly different when you are using the conventional machine learning algorithm, where after defining your features and your target variable, the next step usually involves now splitting into the training set and the testing set. Then after that, you apply your standard scalar. But we're just trying to see how we can apply. We can use the principal component analysis. Then after this, I'm going to do another example where we'll be tackling a real problem. Okay, so xscaled. So we can do xscalar dot fit transform. We are going to transform all our features. So after this, now we have transformed all our features, and they are in the variable x scaled. Then, so let's move on. So let's now import the PCA from sklearn. So this is part of the sklearn library dot decomposition. Import PCA. So when you are dealing with the principal component analysis, earlier on I talked about something about preservation of the variance. So let's expound on that. So when dealing with your PCA, the principal component analysis, we are trying to create or form or draw a hyperplane in the feature space, so that we can try to preserve our variance. So earlier on we say that we are trying to minimizing the sum of square distance between the data points and the hyperplane. So basically, that's what we are trying to, when we talk about the preserving the variance, that's what we are talking about. So before projecting the data to a lower dimension hyperplane, we need to first choose the right hyperplane. And this hyperplane should be that which preserves the minimum variance, i.e., so that we lose less information. So we are trying to find this hyperplane, while in the same time trying to reduce the loss of information. Okay. So we have different methods that we can use while trying to find out this hyperplane, and one of the method is about specifying the variance that you wish to retain. So basically, you're trying to say, maybe I want to retain 100% of the variation in the date, or I want to maintain 99%, 95%, 90%. So that's like an arbitrary value that you're trying to use, so that when I'm going to apply the PCA, is that this is the amount of information that I'm trying to maintain while trying to find the best hyperplane. So with the method where you are going to specify the variance, you'll specify a desired percentage of the variance, so that to explain or use. So with this, we are trying to specify a desired percentage of the variance. Okay. An advantage of specifying this variance is that you can capture a desired amount of variance or optimize performance depending on what you are trying to keep. Then one downside of this is that it can be computationally expensive. Maybe if you're dealing with a high dimension data, then let's say using 99% let's say you want to maintain 99% of your data, then it can be quite hectic when dealing with such data. But let's see if how we are going to apply this method. Okay, so we imported the library for the principal component. Then after this, let's see how we can specify the desired percentage. So get our variable PCA. So PCA, that's the function. Then so when we try to find out the parameters for the PCA, you can see the n components. So this is where you specify the percent of the desired percentage of variance that you want to maintain. So that is the n components. So when specifying this percentage, you use a decimal place. So let's say for me, I will want to preserve the 95% of the variance in the data. Okay. Then after this, we can then pass in our data. So PCA dot fit transform. Then after this, can just say x scale. So x scale is the data that after scaling, this is the variable that stored that data, and we're just recalling that when doing the fit transform using the principal component. So after this, our data will be now in the xPCA variable. So we can check and see how the PCA performed. So earlier on, I'll print the shape of the data before using the PCA. So earlier on we had 112. So remember, we dropped 2 columns. So that means our target as a column is not amongst the features. So you can see we have earlier on, so after scaling, we had 112 features or dimensions. So you can say this. So before applying PCA, so let's say after, so you can say shape after applying principal component. Then after this, you can say x PCA supposed to be so x PCA dot shape. So you can see we have reduced the dimensions, the dimension from 112 to 63. Okay, after using the PCA. So from here we can check about the explained variance. So let's see something about the explained variance and see. So for the explained variance, basically this explained variance explains the proportion of datasets variance that lies along the axis of each principal component. So after applying the principal component, let's see the explained variance tells us about more information about the proportion of the datasets variance that lies along the axis of each principal component that we have used in our data. So for example, given an array of, let's say, 0.825, 0.143, 0.1125, 0.0954. So we'll see how we get these variances. So, but let me explain what the array or the information from that tells us. So when we get an array of different values, this tells us that, for example, for this case, 82% of the data points lie in the first principal axis. So this is the first principal axis, this is the second principal axis, this is the third, the fourth, the fifth, and so on and so forth. So when we convert these values, we just multiply them by 100 so that we can see the proportion. So we can say that the first 82.5 can say that this tells us that 82.5 of the data points in your data set lies in the first principal axis, then 14.3% lies in the second axis, then the third, the fourth, the fifth, so it continues on like that. So as we go on, we'll see that as we go on, consider the principal component has a little information about so you can see that the first principal axis usually has more information than the last principal axis. So let's get the explained variance from our data and see how the figures are looking. So they explained the variance. So the explained variance, so the explained variance ratio. So let's see. So PCA dot variance. So since we used 95%, we wanted to retain 95% of the data. You can see that we have about 63 features. So basically, we are going to have a lot of features or the variance ratio of values. So we are going to now let's print the explained variance for each component. and see. So I'll just use a for loop for I ratio in numerates x. Let's copy this. Just the same ratio. Okay, you can say print explained variance for components. Let's say I and also add another thing. So let's say the ratio. Let's just maintain the ratios to 4 decimal places. So let's say ratio dot 4. I think that's okay. So let's execute this. So these are you can see the explained variance for component 1, 2, 3 until the 63rd component. You can see for the first component, so when we multiply this figure by 100%, you can see that for the first component, you can see that 18% of the data points lie along the first component, and 6% in the second component, about 4% in the third component, 2%, 2%, and when we reach, for the 10th component, you can see it's about 1%. 1% up to around the 36 component, where you can see that only 0.98% of the data points lie in this component. Okay, you can see how you can see from the first to the last, you can see that we have a drop in the data points that lie in the subsequent component, which is to be expected, because most of the times you just want to deal with data that is in a small space. So let's plot a graph to visualize this explained variance and see how. So again, import. So we imported the matplotlib library, I guess so. Yeah, so we just use the matplotlib. So let's say plotting the explained ratio with variance ratio. Okay, so we'll plot, let it be a cumulative one. So cumulative variance, say ratio. So just copy this, variance ratio, and just paste it here. Then we use this function. Then from here, let's plot cumulative explained variance curve. Okay, so figure. So plt.figure, do a fig size, let's say 10,6, is supposed to be in a bracket. I think that's okay. Then plt plot, you can say range say cumulative variance ratio. Cumulative, you can use smaller variable names, but I'm using this detailed one so that they can you can able to see, can able to read along and probably understand what I'm doing. Ratio, then for the marker, for those points, I'll just use say 0. Then we can customize the plot. So from here, okay, so let's execute this. Cumulative variance ratio. So it's to be ratio. Okay, so now with the cumulative explained variance, you can now see how the variance is performing. As between the first and the second, you can see that huge decrease. Okay, then after we saw about 30, we saw that decrease after around 30. So after this, you can now see that these points are relatively very close to each other. Okay, so after this, we can plot a scatter plot so that to see how the separation occurred. So I'm going to plot a scatter plot. So the scatter plot is a useful visualization tool to use. So with the scatter plot, so you can see that we have defined the figure size, then the color codes for the different classes in our target variable. So 0 will be for red, while blue will be for +1. Then we plotted our scatter plot. Then these are just the labels for that. And when we execute this, you can see the PCA scatter plot. You can now see the different classes. Now from the 112 dimension space, we are able to now shrink that, and now you can now see this one is now something that is easily you can easily interpret this. Okay. So that was method 1. It was all about using specifying a % of variance that you wish to retain. So we're going to method 2, which is all about so for the method 2, it's about specifying the number of principal components that you want to maintain. So earlier on we specified the variance. This one is now about the principal component that you want to maintain in your data. So this one, manually you select the number of principal components to extract. So let's say you want 2, 3, 4, or 10. So this is just simple and straightforward. And the downside of using this method is that it may not necessarily capture all the important information in your data. Okay, everything is similar to what we did earlier. So we can just copy this and paste it here. So let's say we want to select 15. Let's keep 15. We want to select only 15 principal components. Then so we can do that. Then we fit and transform. So we can again the shape earlier. Dot shape. So with this, you can see earlier we before using the principal component, you can see that we have a total of 112 dimensions. But after reducing that those dimensions to only 15 components, you can now see when we print the shape after the principal component, after applying the principal components, we can see that and reducing our components to only 15 dimensions. So we only want 15. So you can see we have reduced this to 15. If you want, let's say, to only 5, you can do the same. You can just execute this, and this. You can see we have reduced that to only 5. If you want 20, if you want 7, so it all depends. It gives you that leeway to see which only extract a set number of principal components from your data. Okay. Again, you can also find the explain variance again, which is just a similar thing as to what we did earlier. Again, when we find the explain variance for this, you can also see we're only getting the 7 components after for the explain variance. Okay, so this one you can see how you can move along with this. When it comes to plotting, to determine the cumulative explained variance for that, again, you can see this is the chart for that. You can see the cumulative explained variance again is the number of principal components, and we only selected 7. So you can see 1, 2, 3 up to 7, and you're able to see how the different. So with this line, I think one thing that you can obtain from this line, let's say you are starting with 50, let's say 50. Let's say you're starting with the 50, or let's say the 63 components we got earlier. So with this plot, you are able to select and see which how many components are contributing more to your data, and thereby just selecting those the number of components, the number of principal components that you see, they will be having a maximum effect. Because when we compare, for example, let's compare this. Let's go up to, let's go up to 15. So when we go up to 15, this is the chart we are getting. This is the chart you're getting. As you see, as we increase the number of components, these distances are quite close to each other. And when you compare this to what we got earlier, you can see when we add more and more principal components, we can say something like the effect that those additional components are having on your data. You can see it's decreasing as you increase the number of components. So with this, you can maybe select, and let's say select to the point where the distances between those number of components are decreasing. So you can just do a cutoff and say maybe I'll just deal, or I'll work with this number of components. Okay. Again, if you plot a scatter plot, so when you plot a scatter plot, this is just the same as what we did earlier with those principal components. Again, you can just see basically we're just getting the same thing as we got earlier. Okay. For this method, for the method number 2, when you're just going to specify the number of principal components. So what I was talking about we can use something known as a scree plot. This one is also very important because it's going to help you find the number of components directly. Or for example, a scree plot is a line plot of eigenvalues of factors or the principal components, and this scree plot is used to determine the number of factors to retain or keep in a principal component analysis. So we can use the scree plot. So instead of for example, instead of just using 15, 10, or 20, or instead of just using an arbitrary value, you can plot a scree plot, and from the scree plot you are able to determine the number of factors or the number of principal components that you can retain from the data. So a scree plot always displays the eigenvalues in a downward curve, ordering the eigenvalues from the largest to the smallest. So from this, we'll have an elbow from the scree plot, the elbow of the graph where the eigenvalues seem to level off is found, and the factors or the components to the left of this point should be retained as significant. So we retain those points and consider them as significant, or they have a significant effect on our data. So when we plot the scree plot, for example, we can use the explain variance again. So when we plot this, you can see this is the scree plot, and we're having the principal components as the principal components on our x-axis, while the explain variance on our y-axis. So when we plot the scree plot, earlier we said that the elbow of the graph where the eigenvalues seem to level off is found, and factors, the components to the left of this point should be retained as significant. So where do we have this elbow? I can say we have this elbow because after the fourth component, we can see some leveling off as we increase the number of components. So at this point where we have this leveling off, we can say that only the first four principal components have a maximum effect in our data. So we can just, for example, when trying to, where is it? Yeah. Now we can just, instead of using the 15 or the 95% variance, you can, after plotting this scree plot, you can just now say the first four principal components are the ones that are of more importance, and we should just retain them because of the high significance. Okay, so that's how you can do that. So basically, with this analysis, you have seen how we can apply the principal component analysis. So basically, with this analysis, I will just showing you basically how you can use the principal component analysis to obtain information that this information can be very vital or very important during your training of different machine learning models. So one thing with the principal component analysis that you have seen is that it's very good when dealing with high dimensional data that is in a high dimensional space. So you're trying to at least squeeze that into and obtain only features that are of significance to your machine learning model. So basically, that's all for today. Once again, before we sign off, if you're new to this place, please consider smashing the subscribe button. We are welcoming you to this wonderful community. Hit the notification bell so that you never miss any of our video updates. So, and if you found this video quite informative, you can also like the video and leave a comment behind if you have something to say. We'll get back to you. Once again, thank you for your time and see you in the next one. Bye-bye.